Hello everyone, welcome back to the course on architectural design of ICs. So, in the last few classes we have seen the adder architecture, different type of adders are there, okay, and they are used for different on perspective for different application. Considering the fact that we need that means this speed as a constant or area as a constant or power as a constant. Okay. So, we have seen different type of adder like carry save adder, carry skip adder, and we have started with the basic, that is ripple carry adder, then carry look adder, and then we have seen that okay, we have got, or ultimately we have reached, that means carry select adder, and then from that we have ultimately got to the point that okay, conditional sum adder is one of the adder where it is by that means putting redundant the blocks, how we can achieve, that means the, or how we can maximize the speed of operation of the addition operation. Okay. So, that we have seen in the last few classes. So, now again suppose this adder, why I need this type of adders? Because I said that these adders are required, or this type of architectures or different type of architecture has been evolved because they need for different applications like signal processing application or wireless communication application or biomedical application, everything for the signal processing application. So, that means my point is that suppose if I am doing for biomedical application or one particular hardware I require for biomedical application. So, at that time the power is the major constant, not that speed. On the same way, if I am actually using the adder circuit for wireless communication application, at that time speed is my major constant, okay, because that I have to, that means the more the data rate or the more the frequency I have to achieve there. Okay. So, that is why the two different application require two different type of architecture, because whenever I will follow the architecture which gives me this high speed of operation. So, at that time it cannot gives me this, that okay, it will consume low area or low power. Whereas, the same thing, that means whenever actually we have seen that means we have to lose somewhere to gain something. So, whenever we will try to reduce the power, so at that time obviously that means lesser number of the components I have to use or the basic gates I have to use. So, at that time the lowering the number of components in a circuit, obviously I have to follow this serial architecture, not the parallel architecture. So, parallel architecture I will follow to maximize the frequency, that means if it is for wireless communication application. I will try to reduce the power, whenever I will try to reduce the power. So, at that time I need to use lower number of components or the basic gates, which that means I have to follow the serial architecture. So, that is why I need different type of hardware and different type of, that means hardware of adders we are discussing over here. So, in this whole, that means course, we will see different type of blocks, basic blocks which are being used to design the function which are being used in real time processing or signal processing, wireless communication, that means, or biomedical signal processing. So, any of these application it is used. So, suppose we have seen those architecture. Now, suppose I have to design one running average circuit, which is very much common in any of this, that means signal processing blocks. So, running average blocks means, okay, I will just explain it. So, I have to design one running average circuit. So, how can I do, or what, first the thing is that what is the meaning of running average circuit, and then how can I design one running average circuit in an optimized way, okay, or what are the ways of implementing this running average circuit. So, that we will see now. Suppose I have to average, running average means, first let me explain what is averaging circuit. Averaging circuit means suppose I am having 8 numbers. Okay. So, the summation of these 8 numbers that will be divided by the numbers, how many numbers I am adding. So, divide by that, that is the average circuit, basic averaging circuit. Okay. So, that means suppose if I consider suppose y equals to this y of n, that is if I am considering of 8 numbers suppose, and these 8 numbers are x 7, x 6, x 5, x 4, x 3, x 2, x 1 and x 0. Okay. So, if I need to, that means do the average of this particular 8 numbers. So, at that time how it will be? That will be, it will be x 7 plus x 6 plus x 5 plus x 4 plus x 3 plus x 2 plus x 1 plus x 0 divide by 8. Okay. So, in the hardware, if I want to implement this particular circuit or the corresponding hardware for this particular circuit, so at that time how can I do? Now, consider each of these particular that means bits, that means each of these word length of these numbers, let us consider that are of 4 bit. Okay. So, that means 15 is the maximum number which I can do. So, now if I want to implement this particular function, so at that time how can I do? The parallel implementation is that means for this total how many numbers I have to add, that is 8 number. So, 8 number if I want to add using, that means adder means they are of 2 input, okay, they can consider 2 input at a time. So, considering that fact, how many number of adder I require to implement this? 2, that means first initially what I have to do? I have to add all these numbers, then I have to divide by 8. So, that means to add these 8 numbers I need 7 numbers of adder, and this is the fact that if I want to add n number of adder n number of addition operation, then n minus 1 number of adders I require. Okay. So, here, so how can I implement these things? If I just map it to the, that means corresponding architecture for this. So, at that time this will be something like this. I need initially I need at the first stage I need 4 number of addition, that means adder block, correct. So, this will be x 7, x 6, x 5, x 4, x 3, x 2, x 1 and x 0. So, I will get this sum 3 over here, sum 2 over here, sum 1 over here and sum 0 over here. Then again this particular 4 of this they need to add again. That means again I need 2 adders for adding these 4 numbers. Okay. Then what I will get? Then again I will get S5 and S4 over here. Okay. Then again for this again I need this particular. So, this is my, if I consider this n as, that means 8. So, this is my final output. So, not okay, this is not the final output. What I left, I have to that means do this divide by 8. So, how can I divide by 8? If I, that means write this as the S 6 0 1 2 3 4 5 6. So, if I, that means mention that as 6. So, now y 8 equals to what? S 6 divide by 8. So, this divide by 8 means nothing but the truncation or the of the last 3 LSB position. Why? Because we know that what we know in binary numbers, they are weighted of with the weight of 2. That means, that is for 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. So, the binary numbers are something like this, they are being weighted something like this. So, that means divide by 8. So, if I just discard this particular 3 position, so at that time, so this will be now coming to 2 to the power 0. So, that means I am doing divide by 8 by truncating the last 3 bits. Okay. So, I do not need any extra hardware for doing this division operation. So, this is the corresponding, that means this parallel implementation of this particular circuit. Okay. Now, coming to the point, that means running average means what? So, running average means these particular sets, they are basically changing, and running average circuit, where do I require? That is very much required for one real time signal processing. Okay. So, in real time signal processing, what does that means, what happens? So, that means the samples are changing in real time, that means they are dynamically changing, the number of samples, they are dynamically changing. So, that means now how that means samples are coming like this x1, x2, x3, x4, x5, x6, x7. So, something like this it is coming. Okay. But only what I have to do, only that means these particular things I have to do. So, that means in the first set, if I consider, that means if I just go to there, that means if I consider this is the first set. So, at that time this x7 up to x0 divide by 8, that will be done. In the next, what will be done? That will be x8 plus x1 divided by 8. So, y2 will be what? They will be x9 up to x2 divided by 8. That means, 1 by 1 this will be vanish, okay. And the newer of the samples will be collected in the averaging circuit for doing this particular, that means averaging of that, where this the number of samples they are coming serially to the circuit, and whenever the values of the corresponding incoming the samples, they are changing dynamically. Okay. So, that means now this is the corresponding, that means circuit for, and this is the, that means concept of running average circuit. Okay. So, now here actually one point is there, actually 2 points I have to that means notice, or I have to observe, that is till now what we have, that means seen is that that area, power and speed, these 3 are the major constant while we are doing this VLSI that means circuit design. But there is another thing, which is this accuracy, or this, if I say that the precision. What is that? Because what we are doing, whenever we are talking about hardware, so that means we are dealing with fixed point number system. So, I think this fixed point and floating point number system, that is the basics we have already learned in a digital electronic circuit. Okay. So, this fixed point number system means, that means we have this the watt length that are limited. Okay. So, that means we have to fix initially we have to fix, or we have to, that means finalize that what will be the corresponding word length of the variables or the signals. So, in that means in analog domain or in floating point, what we do? So, what we do? We have something like that means infinite precision. So, that means I suppose this 0.999 value. Okay. Can I represent this 0.99 value in using this that means using binary numbers? Because the binary number is taking only 0 or 1. So, how can I represent then this 0.999 number? I cannot. Why I need to do this? Because in signal processing sometimes what happens, I am repeated, that means the operation they are being used in a loop for, let us consider 1000 times or 2000 times. Suppose these numbers for this particular circuit, suppose this running average circuit I am doing, right. So, each of these numbers they are lesser than 1, and thousands of these I am just adding. So, at that time, if each of these number is, let us consider, fixed to 0.999. So, now if I just add this particular 1000 numbers, so at that time what will be the output? This. Suppose this particular numbers if I want to add 1000 times, so then this will be my final output, this should be the final output. But in this case, if I use this fixed point, that means number representation, so at that time what I will get? Because this x0 to x7 they are not, for any time they will not consider this as 1. They will consider, if that is considered, because they are less than 1, so that will be considered as 0. So, if I consider 0, so 1000 times if I add this particular circuit, it will give me 0 only. So, that means this is the error which I am accumulating. Whenever we are running in a loop and this particular, that means numbers is the numbers are there and they are being, that means running in a loop, that means what I am doing? In each of these stage I am just getting the error of this, and how many times I will run that particular loop, that much of error I will accumulate finally. So, that means this is the error which I am accumulating finally. The same thing if I take one that means another newer example, that means one different example. So, at that time let us consider 1.5, 1.5, 1.5 and 1.5 I have to add, this 4 number I have to add. So, if I just add it just in decimal number, considering decimal number, if I want to add this particular, so at that time what will be y? Y will be 6. So, 6 will be my, or 6 will be my result. Now, considering each of these numbers on that particular circuit, what we have just discussed now. So, if I just add at that time, what will happen? So, at that time what will happen? So, this will not consider 1.5, right. So, this will consider 1, 1, 1, 1. So, this will be 1, 1, 1, 1. So, that means finally I will collect 4. So, that means 2 are the error which I am basically accumulating. Suppose this particular circuit running for 100 times. So, that means 200 will be the error which I will accumulate for running this particular circuit. So, accuracy is also one of the constant which we have to bother about whenever we are doing the corresponding architecture, hardware architecture from the algorithm. So, whenever we are doing the algorithmic verification, so at that time if we consider only floating point number representation, so at that time we will not be that much bother about this particular error accumulation. But as we are doing this fixed point operation in the hardware circuit, so at that time we have to bother, where we have to be cautious, more cautious about how much error I am accumulating whenever I am doing the corresponding particular operation, or that means this internal circuit of that hardware. So, we will take that means many of the that means example. Okay. So, where you can see that how much or how to tackle with, or how to that means do this with or how to tackle this changing of this accuracy whenever we are doing this serial operation, or we are performing the operation in a loop. That we will see in the later of this course. Okay. So, here actually that means for that what I have to do? I have to do this error analysis part. Error analysis, and after that what I need to error correction method. Okay. So, if I just go back to the corresponding circuit, so at that time if I just what I am doing here, I am just why I have just discussed this particular accuracy point, whenever I am just discarding this particular 8 bit finally here. So, let us consider these numbers. Okay. Suppose they are of 5 plus 5 plus, okay, not 5, then 6, then 7, then 8, then 9, then 4, 3, 1, 2, 3, 4, 5, 6, and then 2. Okay. So, what is the number? 11, 18, 26, 35, then 39, 42, 44. 44 divided by 8. So, what will be the, that means number, that what will be the corresponding output of this? That will be 5.5. Okay. So, what I will get if I just add this particular from this particular point, if I just do this, so I will not get, so 44 means what will be its binary number representation? So, 32, then 8, then 4. So, this will be the corresponding binary representation of 44, right. So, now what I have to do, whenever what I said that I have to discard the last 3 LSB position, okay, for as I am doing this divide by 8. So, here in this number, that means this is my S6, right, this 44 is my S6. So, now what I have to do? I have to discard this particular 3 bit. So, now what value I am getting? 0, 1, 0, 1. So, 1, 0, 1 means 5, but what is my result? That is 5.5. So, that means this 0.5 is the error I am accumulating for truncation of this particular block. Okay. Now, if these circuits, what I said, now if these circuits, if I run it for 1000 times in a loop, so at that time in each of this state or each of this loop I am accumulating 0.5. So, that means now 0.5 means 500 is the amount of error which I am accumulating if I just run this particular circuit in a loop. Okay. So, this is the running average circuit, and this is the problem in corresponding running average circuit whenever we were doing. Now, this is the, that means this the corresponding parallel implementation, right. Now, for this, suppose what I said that I have to do this 1000 number of addition operation. that means this number of samples which are coming at this flow, there I have to do the running average of this 1000 number of samples. So, at that time for the whole process, the total computation time for running average circuit, that means doing the running average of this 1000 number of samples, what will be the computation time for that? If I consider this each of these, that means delay for this adder, there let us consider of 5 nanosecond, and I need to put the resistors over here. For each of this there will be, that means each of the input side there will be resistor, and the output side the resistor also will be there, right. So, this is the input resistor, this is the output resistor. So, if these resistors requires 1 nanosecond of delay, okay. So, at that time so, at that time what will be my total computation time for doing the running average of 1000 number of samples. So, that means let us consider each of the samples is coming after 1 nanosecond. Okay. So, that means the sampling speed. So, now if I just draw the block of this is the running average blocks, correct. Now, x is coming, x is the input which is coming and y is the output I am getting, right. So, now x is coming what? They will also have some clock frequency, okay. So, that means now this is coming, or this sampling speed of this there, if I that means consider that as 1 this gigahertz. So, that means each of the samples are coming at 1 nanosecond of time. So, if I consider this 1000 number of samples, for doing the running average. So, at that time how much time I have to wait for all the samples to come to this particular circuit? There will be 999. That means, after 99 I will get the output of y. Now, apart from that, what I need? I have to consider the corresponding delay of each of these stage, that means the corresponding adder delay for these 3 stage, that also I have to consider. So, what I require, that means 3 number of stages are there, that means 3, and each of the adder delay is 5. So, that will be the corresponding delay, and what I require, that means what else I left, that are the corresponding delay for this particular resistors, input resistors and output resistors. Okay. So, then 2 of them I am using. Why 2 of them? That means I am using 8 at the input side and 1 at the output side, but 8 at a parallel. So, each of these is that means consuming 1 nanosecond delay. So, that means the maximum of that will be the delay for that resistor. So, maximum is 1. So, I am considering 1 for the input delay and 1 for the output delay. Okay. So, into 1. So, that means now 999 plus 15 plus 2, that is equals to 1016. So, this time I require to complete the whole process of 1000 number of samples running average. Okay. So, this is that means parallel implementation if I chose. So, at that time this will give me this. Okay. So, then again this is the that means if I consider, then that means what I am getting, the computation time is 1016 nanosecond. Okay. Then the hardware requirement is 7 number of adders, each of are not 4 bit, that will be 4 bit. In the next stage it require 5 bit, and in the next stage it require 6 bit. Okay. So, why I need to do that I will also not here. So, it will consider 4, 5, 2 bit I will have 6, here 7, this will require 8 bit. So, why I require 8 bit, that I will come later. Okay, not 6, 7, 8. Okay. So, what will be the corresponding bit size, then again I will discuss on that. Okay. And then total 8 plus 1, 9 number of registers I require as the hardware requirement. Okay. So, if I consider this particular circuit, that means the that parallel architecture. So, at that time this is the number of that means this is the total computation time, and this is the hardware requirement of that, but this for this corresponding circuit. Okay. So, for today this is it. Then again we will discuss or we will that means see different architecture for this particular operation. Okay. So, that we will see in the next class. Thank you.